Hey, ladies and gentlemen, this is Mr. Los. Thanks for tuning in again to the flipped lesson. Today we're going to talk about radioactivity. As always, when we do these lessons, I'd encourage you to pause the video from time to time, take notes, rewatch stuff if you need to, and of course, next time we see each other in person, let me know if you have any questions, or reach out to me via email or Teams. So let's get cracking here. We're going to talk about radioactivity, as I said, and when people hear about radioactivity, if they know anything about it at all, they think about scary stuff like mutant fish and the Ninja Turtles and explosions. But I bet if you talk to a lot of people out there, adults, really anyone, and they might be scared of radioactivity, but if you actually asked them what it was and asked them to define it, I think a bunch of people out there would have a really hard time actually defining what it is. So that's what we're going to learn. We're going to educate you. You shall no longer be ignorant when it comes to what radioactivity actually is. So radioactivity actually does have a bunch of positive uses. You can generate electricity from it. Of course, you can make bombs from it. That's maybe not so positive. You can do some imaging like X-rays. And what you're seeing here is another way we use radioactivity to image things. The element thyroid is needed by the element iodine is needed by human beings in really tiny amounts. And in our salt in this country, we actually intentionally put in just the tiniest amounts of iodine. And what that does is it helps thyroid function, and it prevents a condition called a goiter. And a goiter is where you get this huge swelling in your thyroid glands, which are in your neck. Does not happen in the developed world very often, but in the developing world it does happen. So anyway, point being, the element iodine does sort of collect in your thyroid, and what doctors do is they inject a radioactive version of iodine rather, and it ends up collecting in a patient's thyroid, and it can do some imaging. And if you're a doctor, you can look at these images and kind of know what you're seeing, and you could do things like diagnose hypothyroidism, hyperthyroidism, thyroid cancer, and things like that. So it's a way we use a radioactive isotope of an element, iodine, to help get pictures of the interior of our body. So kind of like an X-ray, but an even fancier thing. So like I said, a lot of people don't actually know what radioactivity is, so let's talk about it. Things that are called radioisotopes are unstable isotopes of an element that emit rays or particles till a more stable element is achieved. Any unstable isotope is considered to be radioactive. So is radioactivity dangerous? It definitely is if you're talking about ionizing radiation. It's dangerous, especially when you're exposed to it in large quantities. What is ionizing radiation? It's radiation that has enough energy to knock electrons off atoms, which will create an ion. That's where that word ionization comes from, because ions are charged particles. So if ions are being created like where they shouldn't be, or in the interior of your body, that can eventually cause damage to other cell structures, to DNA, and you can definitely have some problems with that. So the types of radiation that we're going to be talking about, which are alpha and beta particles, plus electromagnetic radiation, the ultraviolet range, talk more about that in a second, are examples of ionizing radiation. So this stuff here is not important in the sense that this is not necessarily things you need to write down for your notes for the purposes of this class, but I just want to talk about this from a perspective of just your knowledge and things you might hear about. People used to say, you don't hear it quite as much, but people used to always say that cell phones cause cancer. I hear people say that Wi-Fi signals cause cancer or cause problems of some kind. So what we see here is the whole electromagnetic spectrum, which goes from radio waves to microwaves, and this little part that we call visible light and all of that. So cell phone and Wi-Fi signals are carried by radiation, electromagnetic radiation, down here in the radio/microwave end of things. So remember, the whole electromagnetic spectrum, it's all the same stuff, just different wavelengths and different frequencies. Radio waves and microwaves are around 100,000 times less energetic than even visible light. And they're 1,000,000 times or more less energetic than the actual part where it starts to get dangerous, which is right about here in the ultraviolet range. And you've heard about ultraviolet light causing skin cancer and things like that. So both Wi-Fi signals and cell phone signals are much, much, much less powerful. So they're less powerful, less energetic than even red light. So if cell phone signals and Wi-Fi signals are dangerous, well then red light would be incredibly dangerous because it's 100,000 times more powerful. But of course, red light isn't dangerous, and I don't think Wi-Fi signals and cell phone signals are dangerous either. They're way, way, way below the energy necessary to be what we call dangerous ionizing radiation. So we're going to talk about basically three main types, two really, that we're going to focus on especially. One of them is alpha particles. Alpha particles are helium nuclei without any electrons. They're 2 protons and 2 neutrons. They have a +2 charge because they have no electrons. You'll see the symbol for them written a couple different ways. That's the Greek letter alpha right there. There's also beta particles, which is kind of a high energy electron that goes shooting off. Its symbol is this, 0, -1e, or this. That's the Greek letter beta. And then also gamma radiation, which is very, very high energy ultraviolet, higher than ultraviolet, very, very high energy electromagnetic radiation, so higher than X-rays, the highest of all. They're massless because they're like light. They're just electromagnetic radiation, except much more energetic than light. So this, again, no need to write this down, but this is just an overview of the type of radiation that you might get, or the dose of radiation in milliriems a year. That's just a unit for measuring radiation. So there's radiation all around us. There's those particles I mentioned, alpha, beta, gamma. There's some in the room right now going right through you at this moment. Well, alpha particles don't go through you, but nor does beta. But there's radiation all around you. There's alpha particles bouncing off you and all that kind of thing. There's the rocks beneath us are radioactive. There's all kinds of radioactive sources. So even just living and existing, you're going to get exposed to a certain amount of radiation from all sources. So this is all sources. This is quote-unquote natural sources, so just the rocks and things like that. You might get an X-ray and all that kind of thing and get exposed to a little bit of radiation. Notice that people are really scared of nuclear power, but notice that the dose, coal-burning power plants actually expose people in the neighboring community to more radiation than people who are near nuclear power plants. This is because there's radioactive stuff even in coal. So you take it and you burn it in the coal-burning power plant. It goes out the smokestacks. It gets spread out far and wide. Nuclear power is scary. It does have potential to cause some big problems, but the amount of pollution that nuclear power produces is much, 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 much less than coal-burning power plants. It's just the very tiny amount of pollution it does produce is particularly bad. But in terms of like a climate change perspective, nuclear power is much better than coal-burning power plants, and is something that we may need to think about expanding if we are concerned about climate change going forward. Just some other sources of X-ray, just for your interest, different doses that you might get. I'll talk about the fluoroscope in a second here. And again, not important, just a fun fact. Back when people were first learning about radiation, they didn't really realize how dangerous it was. So people do all sorts of crazy things with it. But one thing, like in shoe stores, you could literally step up on this box, put your feet in it, peek down through that hole and see your bones and wiggle them around. So this was supposed to see if your shoe fit. So meanwhile, exposing you to a huge dose of radiation, and also the people who worked in the store to a huge dose of radiation. So probably not worth it in that case. Obviously, those have stopped being used. But just an example of one of our misunderstandings of the use of radioactivity in the past. Okay, so back to stuff that we probably should have in our notes. These different types of particles have different types of penetrating power. In other words, they can go through more stuff. Alpha particles are mainly going to be stopped just by your skin or a thin piece of paper, so they would bounce right off a piece of paper, for example. Beta particles would be stopped by, a really thick sheet of aluminum foil, or maybe a couple of those. They'd bounce off of that. Gamma rays are really powerful, and they can go through quite a lot of stuff. About a meter of concrete, as it says here, at least. Now, if you think about X-rays, like when you get an X-ray at the dentist and you wear that lead vest, X-rays aren't as powerful, so you don't need as thick of stuff. But they're putting that lead sheet on your chest just to limit the exposure to radiation that you're getting as much as possible, because there's a risk even in dental X-rays of getting cancer or causing problems. So they're just trying to minimize that risk as much as possible by putting you in that lead vest. So X-rays could be stopped by a thin lead sheet, but gamma rays are more energetic and take more. Again, nothing you need to write down or know for sure, but just if you're getting a huge dose. Notice the previous slide was millirems. This is rems. This is getting a dose kind of at once of huge amounts of radiation. So as you go up and up and up, the problems become worse and worse and worse until if you got a super large, exposure to radiation in one shot, like if you're on the outskirts of a nuclear bomb and weren't destroyed by the bomb itself, a huge blast of radiation might kill you. Something like that. So yeah, a large enough dose of radiation at the same time could kill you right away. A smaller dose might give you cancer or something like that and just kill you later. Or nothing might happen. It's all just chance. So what happens is if when we say, like I mentioned earlier, if a nucleus is unstable, and it becomes unstable because it has a improper ratio of neutrons to protons. It's not 1-to-1, but there's certain ratios of protons to neutrons that are more stable. So an atom is going to be radioactive if it has an unstable ratio. And what that atom will do is emit either alpha or beta particles or sometimes some other things that we're not going to get into too much until it reaches a more stable state. So you write what's called a nuclear equation, and it looks like this. And one thing that's true about nuclear equations is they must be balanced, meaning the masses on the left have to add up to the masses on the right. So, for instance, here we have uranium, uranium-238, we call it, and it's unstable, it's radioactive, it's one of the most famous radioactive isotopes around. It emits an alpha particle, and then that atom will turn to the element thorium, because it has 2 fewer protons at that point. So what I mean by balanced is 234 plus 4 is 238, 90 plus 2 is 92. So both sides add up to the same thing. A beta particle happens when a neutron turns into a proton. It's called beta decay. Again, the equation has to be balanced. So 137 plus 0 is 137. That's good. 56 plus -1 is 55. So it's kind of like we're subtracting 1. And it changes into a different element. So instead of being cesium, the unstable cesium isotope will actually turn into barium. And over a long period of time, all of the cesium would eventually turn into barium. So we can write these equations like this relatively easily. You do need a periodic table. If you don't have a periodic table handy, you may want to pause it and grab one. Supposing I'm going to fill in that block right there. So it has to be balanced. So basically it is some number plus 4 is 202. Well, that would be 198. And then some number plus 2 equals 82, so that would be 80. So now my equation is balanced. 198 plus 4 is 202, 80 plus 2 is 82. And then here's where I need my periodic table. I look for the element that has the atomic number of 80, and that would be mercury. So that one's all done, and there we go. There's the answer, and there's the completely written one out that way. So let's look at another one here. We have 126 over 50, 10, and again, it's emitting an alpha particle. So trying to, and you don't need to write down all these examples, by the way. A couple is probably fine. So some number plus 4 equals 126. Some number plus 2 equals 50. Well, that would be 122 over 48. And then once I realize it's 48, I can look up element 48 and see that it's CD. So here's a beta particle this time. Okay, so some number plus 0 is going to be 81. Well, that would, of course, be 81. And here's where it's a little bit tricky. Some number plus -1 equals 36. If you think about it, that would have to be 37, because 37 plus -1 is 36. And again, we can look up and see that that's rubidium. Why don't you take a second and you can try this one. Okay, and we can see the answer there. So here's one where instead of now the particle is missing, so we got to figure out what that particle is. And you can see there must be a 4 here and a 2 there. So that would be an alpha particle. So hopefully that's not too challenging, but let me know if you have any questions, and we'll get those addressed next time I see you. If not sooner, if you email me. Here's a couple other particles. You don't really you're not going to be tested on any of these. You may run across some if we do some practice. It's just there kind of for your reference. But there's alpha particles, radioactive elements can shoot off just a neutron or a positron, which is a positive electron. It's the antiparticle to an electron. Or a proton, they can shoot off a proton. So just a couple different emissions that you might see from a radioactive atom. So what actually happens sometimes is a radioactive substance will emit an alpha, beta, or some other particle, and they'll turn into a new isotope, which is still not stable. And then that thing will emit another alpha or beta particle or whatever and so on. And this might go through a whole series like this. Now, you do not need to write this down, but just as a quick example, if we start out with radium, for example, it might emit an alpha particle, and it turns into radon, and another alpha particle, and it turns into a polonium isotope, and so on. So we can see it's going to go through this huge series till it finally ends up with lead. And these have different half-lives, which we'll talk about in a second, but that has to do with how unstable they are. So the shorter the half-life, the more unstable. So this has a half-life of 1,600 years. This has 3.82 days, and so on. This one is just in milliseconds, so it has a very short half-life. So it would eventually, after a very long period of time, all this radium would eventually turn into a stable isotope of lead. So I mentioned half-life. You've probably talked about this before in some other classes, but a half-life is the time necessary for half the radioactive material present to decay to other products. So it goes down by half each time. So for example, we have this radioactive isotope of oxygen here. We start out with 20 milligrams of it. After one half-life, we're down to 10, and then we're down to 5, and then we're down to 2.5, and so on. So it gets cut in half every single time. And the half-life looks to be about 2 minutes. So it takes about 2 minutes, however much you're starting with at the beginning of that period. After about 2 minutes, it'll be half of what it was before. And it keeps getting cut in half again and again and again. And, you can use this to date old materials. So like, for example, you don't need to write down this question. Just this is something for you to see how it works. Suppose 2 grams of a radioactive material exists. How many grams of the material will remain after 3 half-lives have passed? So, there's a couple ways to do this. There's an equation, but we can just think about it. After 1 half-life would be 1 gram. After 2 half-lives would be 0.5 grams. And after 3 half-lives would be 0.25 grams. So I'm simply cutting it in half every time. Again, another question. You don't need to write this down, but why don't you just read it and think about it for a second and pause the video and see if you can figure this out. Okay, so the answer is 2,000 years, and it helps to diagram it out like this. So we're starting off with 1 gram, and after 1 half-life, there'd be 0.5 grams, and then after a second half-life, there'd be 0.25 grams. Some people want to call this 3 half-lives, really, but there's only 2. So that'd be 2,000 years. And this is a very simplified example of how you can use radioactive materials to actually date and figure out how old fossils are and things like that, because they decay at a very predictable rate. So let's think about this one. Again, another question. You don't need to write this down, but just another example. A certain radioactive material has a half-life of 6 minutes. If we begin with 10 grams of the material, how many grams remain after 18 minutes? I'd like you to see if you could figure this one out on your own. But start by thinking about how many half-lives will pass if the time is 18 minutes and 1 half-life is 6 minutes. So you can pause the video for a moment and see if you can figure that out. So 18 minutes divided by 6, that means 3 half-lives have passed. So we need to divide this number in half 3 times. So we divide it in half once, we get 5. Again, we get 1.25, 5 to 2.5 to 1.25 at the end. And that's how much would remain. And as I said, this can be used to date old rocks and fossils and the like. So that's all I have to say. Thank you very much for watching, folks. As I said, reach out with any questions you have, and we'll see you next time.